Hello and welcome. Today we'll be looking at the DS28E18 one-wire to SPI and I2C bridge device and its evaluation kit. Now, one-wire isn't quite as well known as SPI and I2C, but it's a really useful interface technique, and especially for remote sensing applications. Here's why. First, range. I2C can be used in cables that are no longer than a few meters, and SPI is generally limited to less than 1 meter, but one wire can be extended over cable runs as long as 100 meters or even more. And about that cable, how many conductors are needed to make the connection? Well, with I2C, there have to be 4 conductors: power, ground, SCL, and SDA. With SPI, it's even worse. Power, ground, MISO, MOSI, the bit clock, and slave select. That's 6 wires. But one wire just needs a single wire plus ground, just 2 conductors. Power for the interface and the sensors are derived from the single data wire using a system called parasite power. But, like every engineering solution, there are trade-offs. I2C interfaces typically run at one of 3 data rates: 100 kilobits per second, 400 kilobits per second, or a megabit per second. And there are higher speed options that require more specialized hardware. SPI, though, can run pretty much as fast as you can clock the logic, with speeds of a few megahertz now common. But one wire, it's not really built for speed. Standard speed one wire runs at 11 kilobits per second, and there's an overdrive mode that delivers 90 kilobits per second. But we're talking about sensors here, and sensors generally deliver just a few bytes of data per sample at relatively low sample rate. So you don't often need megabit interfaces. A few kilobits per second will comfortably get the sensor data where it needs to be. That's the strength of one wire. It gets the data from where it's created to where it needs to be, with a minimum of hardware in between. Now, despite the advantages of one wire for connecting sensors, many types of sensors only support I2C or SPI, and that's where the DS28E18 comes in. With the DS28E18, you can connect your I2C or SPI sensors to a one-wire network. Now, if you know anything about I2C, SPI, and one-wire, you understand that they're all quite different protocols that handle things like message delimiting and device addressing very differently. It's not sufficient to just take the data stream on a one-wire interface and blindly send it to a SPI or I2C interface. For example, how would you signal a start or stop event on a one-wire interface when one wire has no concept of start or stop events? Or how would you signal to assert or deassert slave select on a SPI interface when one wire has no concept of an independent slave select signal? Well, that's the reason we've included a command sequencer in the DS28E18. With the command sequencer, you can tell the interface when it should send a start or a stop, or when it should assert or deassert slave select, and when it should add delays to the command sequence. The command sequencer supports automatic programs up to 512 bytes in length. Hey, that's a lot of stuff to squeeze into a tiny 8-pin package. But enough talk. Let's get to the fun part. Here is the DS28E18 evaluation kit. This collection of modules looks kind of like a little train, but each module has a specific purpose. Let's take them one at a time, right to left. The first module is a USB to one-wire adapter. Now, to a PC, it looks like a serial port, and it converts incoming data to one-wire commands and returns data from the one-wire bus back to the PC. The second module is the DS28E18 itself. On the right is a 6-pin connector, but really only 3 pins are used: the one-wire connection, ground, and power for ancillary purposes like running the LEDs. On the left is a standard PMOD connector that expresses the I2C and SPI interfaces. Now, one note. There are only 4 I/O pins on the DS28E18, so the SPI and I2C interfaces have to share some pins. That means you can't use the SPI interface and the I2C interface at the same time. You have to configure the DS28E18 to run either in SPI mode or in I2C mode. In our demonstration, we're going to be showing off both modes. The third board is a temperature sensor. Now, it uses a DS7505 temperature sensor device with an I2C interface. As you can see here, there's not a lot going on, just the sensor and a bypass cap, and well, that's it. The fourth board is also a temperature sensor, but it uses a MAX 31722 temperature sensor device with a SPI interface. Now again, notice that this is a pretty minimalist board, just the device and a bypass cap. Now, having all this cool hardware without any software to drive it wouldn't make any sense, and Maxim has built Evaluation Kit software to show off all the features of the device. You can download a copy for yourself from Maxim's website, and when you do, here's what you'll see. At the upper left is a space reserved for the list of one-wire devices. Just below that is a box for reading the temperature for one or the other of the temperature sensors, and we'll come back to that in just a minute. The next 3 blocks, labeled Sequencer Commands, Sequencer Memory List, and Device Function Commands, manage the sequencer. You can use the Sequencer Commands box to populate the memory list, then use the Device Function Commands to write the memory list to the device, or read the memory list from the device, or run the sequence of commands. The final 2 boxes on the right manage the one-wire interface. The top combo box manages the speed of the one-wire interface, either 11 kilobit per second standard speed or 90 kilobit per second overdrive speed. The second box, ROM function commands, determines which function to use in addressing the devices on the network. Well, since there's only a single device on our network, we can use the skip ROM command. Now, if we had more than one device, we could use match ROM to explicitly declare which device we were addressing. Okay, that's the one-wire to I2C SPI tab. Now let's switch to the other tab, the Settings tab. Here, on the left, we find boxes left over from the first tab, the device list, one-wire speed, and ROM level commands, as well as some new settings for device and GPIO. The device settings set the generic options for the DS28E18. Here you tell the device at what speed it should operate, whether NAC events should be ignored for I2C, whether to configure the I/O pins for SPI or I2C, and what SPI mode to use. The DS28E18 will support either Mode 0 or Mode 3. The GPIO box has all the controls to manage the GPIO pins of the device. You can configure pull-up, slew rate, output levels, and input buffer configuration. Note that for either the device or the GPIO settings, when you click Execute, the command runs right away. It's not transferred to the sequencer. Okay, let's click back to the one-wire to I2C SPI tab. Notice that the device list box is currently vacant. Well, we're going to fix that. Just click on Find Devices, and when the command completes, you'll see that one device has been found. Wait. One device? I thought we had at least 2 temperature sensors on the network. Well, yes and no. We do have 2 temperature sensors out there, but the temperature sensors aren't one-wire devices. They have SPI and I2C interfaces, remember? There's only a single one-wire device on the network, and that's the DS28E18 itself. The one-wire master has conducted a standard search for one-wire devices and has come up with this one, and that's exactly what we expect. Now, if you scroll up through the log window, you can find the exact one-wire commands that were sent to enumerate the devices on the network. But for our purposes, it's sufficient to note the final outcome. The last command succeeded, finding a device in I2C mode, running at 400 kHz, and ready for action. Notice, though, that we don't know if a temperature sensor is actually connected or not. All we know is that there's an I2C interface out there, and if there's a DS7505 sensor attached, we're ready to read it. Well, let's try that. Click on Get Temp, and you'll see a flurry of activity in the log window, but at the end, you'll see the ambient temperature. Now, when we scroll up, we can see the exact sequence that got us to the temperature reading. First, the EVKit software sends a command to configure the DS28E18. Now, this isn't strictly necessary. After all, the DS28E18 is already configured for I2C operation. But hey, it doesn't hurt. The one-wire command sequence begins with a bus reset along with a wait for a presence pulse that lets the one-wire master know that there's a device out there. Then the master sends hex CC. That means skip the ROM stage and proceed directly to a one-wire command, and that command is hex 66, command start, followed by the command length, 2 bytes. Now we're ready for the actual command, hex 55, write configuration register. And it's written with the value hex 01. That sets the interface to I2C running at 400 kHz. Next, the EVKit software programs the command sequencer with a set of commands that will be sent on the I2C bus to the DS7505 temperature sensor. The sequence starts pretty much the same as the previous command. You see the hex CC for skip ROM, then hex 66 for command start, then the command length. This time it's hex 1F or 31 bytes. The command this time is hex 11. That's a write sequencer command. The next 2 bytes are the starting address in the sequencer RAM. We're starting at the beginning address 0. The rest of the bytes on this line are the actual bytes that will be sent to the sequencer, and we're going to delve more deeply into those in just a moment. The third one-wire command is hex 33. That's run sequencer. It has 3 bytes as parameters. A 9-bit starting address that consists of the first complete byte and the low-order bit of the second byte, and a 9-bit length consisting of the high-order 7 bits of the second byte and the 2 low-order bits of the third byte. The rest of the third byte's unused. When the sequence is finished, the temperature that was read from the sensor will be stored in sequencer memory. The final one-wire command is hex 22. That's read sequencer memory. And I'll bet you can guess what it does. Yeah, that's right. It reads the temperature from the sensor that's been stored in sequencer memory. That's what was interpreted and displayed in the log window. Now, we can do the exact same thing, but with a SPI-based sensor. First, let's go over to the Settings tab and switch the interface to SPI. When we click Execute, the command is sent to the DS28E18 and the I/O pins are reconfigured to create a SPI interface. Now, when we go back to the Main tab, we see that the MAX31722 sensor is selected in the temp sensor box. And when we click Get Temp, you see something very similar to the sequence you saw with the DS7505 sensor, but notice the configuration byte has changed. It now sets the interface for SPI, operating in mode 3. So we can see that we're addressing the MAX31722 sensor and not the DS7505 sensor. Okay, that's all well and good, I suppose, but these are still just canned demonstrations. How can we actually use the sequencer to create our own sequences? Well, It turns out to be pretty easy. Let's switch back to I2C mode. Go to the Settings tab, select I2C as the protocol, execute the selection, then switch back to the Main tab. Now, before we start programming the sequencer, let's talk about what it is we want to do. First, we need to talk about the DS7505 temperature sensor. It contains 4 registers, but we really only care about 2 of them in this application. At address 1, there's a configuration register that we need to load with the value 0 in this application. And at address 0 is the actual temperature value that we want to read. The device address is hex 90. So, here's how we program the sequencer. First, we need to power on the sensor. Hey, we won't be reading very much data from the sensor unless we apply power. Next, we delay a millisecond just to let the sensor get ready to respond. Then we send an I2C start condition, and then we send the address of the device, hex 90, and we're going to leave the least significant bit as 0 to indicate a write operation. Next, we specify the sensor configuration register at register address 1 and load it with the value 0. After that, we send a repeated I2C start condition. Again, we send the device address, but this time we specify the temperature register at address 0, and then we write 0 to it. Now, I've got to explain. Writing to the temperature register doesn't actually do anything. We perform this write just to move the internal address pointer back to the temperature register in preparation for the temperature read step that's about to come up. After that write operation, we send a stop condition and program a delay for a half second. Now, while we're waiting, the DS7505 is making temperature conversions. The conversion time for a 9-bit temperature reading is only 25 milliseconds, so in the half second we wait here, the DS7505 is going to make some 20 measurements. Now, we can read the temperature register at any time because the data is protected from corruption if we read while a conversion is in progress. But when the delay time expires, we send a start condition, then a write data command, but this time we're sending just 1 byte, the device address, hex 90, with a low order bit set. That makes it hex 91, and that indicates a read operation. Next, we send a read data command, but notice that we'll knack the last byte to indicate to the DS7505 that we're done reading data. And we're reading 2 bytes. Now, when I add this command, notice what shows up in the sequencer memory window. Yes, there's the read data command. Yes, there's the length. But then comes 2 bytes of dummy data. That's where the data we read from the sensor is going to be stored. Okay, so now that we've read the data, there are just 2 more things we got to do. Send a stop sequence and turn off the sensor power. Now the sequencer program is complete and it's stored in the application, but it's not yet been transferred to the device. To send it to the device, just make sure Write Sequencer is selected and click Execute. That sends the sequencer program to the DS28E18. And now, we're ready to run the sequence. To run the sequence, just click on Run Sequence and then Execute. You'll see the now familiar flurry of activity in the log window, but at the end, the one thing you won't see is the temperature. To get that, we need to perform one more action. We need to read the result from those 2 dummy bytes that we set up earlier. Change the address range from hex 18 to hex 19, click on Read Sequencer, and then click Execute. In the log window, you'll see the read data. In this case, hex 17 followed by hex 80, indicating 23.5 degrees Celsius. So that's how you use the sequencer. Just use the buttons in the sequencer commands window to add commands to the sequencer memory list and let your imagination run wild. Now, there's one more thing to cover. In SPI mode, you're using all 4 I/O pins on the DS28E18 for communications, but in I2C mode, you're just using 2 pins. And that leaves 2 pins as spares that you can use for whatever you want. In this case, I've installed a couple of jumpers on the board to connect the 2 spare GPIO pins to the LEDs. Now, on the settings page, we can send commands to turn on and off the GPIO pins. And as you can see, when we click execute, the LEDs obey the commands that we've sent. So that's a brief introduction to the DS28E18. It's a clean, simple way to extend the range of wired sensors regardless of the interface they use. Hey, stay tuned for more innovative products from the minds at Maxim Integrated.